Do you know how electricity travels hundreds or even thousands of kilometers from power plants to cities? Today we're going to explore the incredible engineering behind high-voltage transmission lines, the massive structures responsible for carrying electrical energy across entire countries. In the early days of electricity, power plants only supplied nearby communities. Energy didn't need to travel very far between where it was generated and where it was consumed. But as cities expanded, industries grew, and populations spread across huge territories, power stations became larger and more distant from urban centers. This created a major challenge. How could enormous amounts of electricity be transported efficiently over extremely long distances? Connecting entire cities to power plants is far more complex than plugging an extension cord into a wall outlet. Generating electricity is already a massive industrial operation that requires billions of dollars in infrastructure, maintenance, and operation costs. Once the electricity is produced, it must safely travel through mountains, forests, rivers, deserts, and isolated regions before finally reaching homes and businesses. That's where transmission lines become essential. Transmission lines are specifically designed to transport huge amounts of electrical energy at extremely high voltages over long distances. In Brazil, for example, one of the country's largest transmission lines stretches more than 2,500 kilometers, crossing multiple states and dozens of cities while carrying power generated at the Belo Monte hydroelectric plant in Para to the southeastern region of the country. To make this possible, engineers must carefully solve several technical challenges. One of the first is choosing the conductors, the cables responsible for carrying electricity. The main requirement for these conductors is low electrical resistance, which is why transmission lines typically use aluminum or copper. If electricity is difficult to move through the cables, part of the energy is lost as heat before it ever reaches consumers. You can actually observe a small version of this phenomenon inside your own house. When you turn on a high-power appliance such as an electric shower or hair dryer, lights may briefly dim. This happens because the wires experience a voltage drop caused by electrical resistance. In transmission systems, this same effect exists on a much larger scale. The power lost in a conductor depends heavily on the electrical current flowing through it. According to physics, power losses increase proportionally to the square of the current. This means that if the current doubles, energy losses become 4 times larger. Engineers therefore needed a way to reduce current while still delivering the same amount of power. The solution was increasing voltage. This is one of the most important principles in modern electrical transmission systems. Substations located near power plants use massive transformers to raise voltage levels before electricity enters the transmission network. In some cases, the voltage is increased to hundreds of thousands of volts. By using higher voltages, the electrical current becomes much lower, dramatically reducing energy losses during transmission. However, increasing voltage introduces another challenge: safety. At extremely high voltages, electricity can jump through the air itself, creating dangerous electric arcs. Because of this, transmission lines require enormous distances between conductors and structures. Surprisingly, most high-voltage lines do not use thick insulation around the cables. Instead, engineers rely mainly on air spacing and specialized insulators. The conductors are attached to towers using long chains of ceramic or composite insulators that keep energized cables safely separated from the grounded metal structures. In many cases, you can estimate the voltage level of a line simply by counting the number of insulator discs attached to each conductor. Transmission towers also come in many different shapes and configurations. Their geometry depends on factors such as voltage level, number of conductors, mechanical loads, and electromagnetic effects between phases. The height of the towers is carefully calculated to prevent vehicles, trees, or people from approaching close enough to create electrical arcs. Most transmission systems use 3-phase power, which is why conductors are typically arranged in groups of 3. You may also notice smaller cables running along the very top of transmission towers. These are shield wires, designed primarily to protect the main conductors from lightning strikes. When lightning hits the line, these grounded wires safely redirect the electrical energy into the earth. Designing transmission lines is not only an electrical engineering challenge, but also a mechanical and economic one. Every component must balance strength, efficiency, durability, and cost. Since transmission systems can extend for thousands of kilometers, even small changes in conductor size or tower design can dramatically impact the total project cost. The towers themselves must withstand extreme weather conditions, including strong winds, storms, temperature changes, and even earthquakes in some regions. Each tower requires specially engineered foundations adapted to the soil conditions along the route. Rocky terrain, wetlands, forests, and mountains all demand different construction solutions. Environmental and legal challenges also play a major role. Transmission lines often cross protected forests, rivers, farms, and private lands. Before construction begins, companies must go through extensive environmental licensing processes and negotiate land use agreements with property owners. Delays caused by environmental restrictions or legal disputes can sometimes postpone projects for years. Despite all these difficulties, transmission lines remain one of the greatest engineering achievements of modern civilization. Without them, large cities, industries, hospitals, transportation systems, and the internet itself simply could not function. Every time you turn on a light switch, charge your phone, or use an appliance, you are relying on an enormous network of high-voltage infrastructure silently operating in the background. Transmission lines may seem simple at first glance, but behind every tower lies a combination of physics, engineering, logistics, economics, and environmental planning working together to keep the modern world powered 24 hours a day.